In this lesson, we'll take what looks like a minor departure from our examination of polynomials and look at the binomial theorem. Now, this isn't a complete departure because this will help us to be able to recognize patterns that exist inside of the binomial or inside of polynomials through binomial work, but it does take a little bit of a different approach to it. We will later come back and revisit this when we look at probability systems that will help us to find some of these values a little bit more quickly. But to begin with, we're going to expand the binomial a plus b to the n for n values of 0 through 5. Now to do this, we're going to make a table, and for it we're going to pick our n, our expression, before expanding. Then we're going to expand it. And the last thing is we're going to take a look at the coefficients. And that coefficients really becomes the vital part of what we're looking at. So for n being 0, we have a plus b to the 0 power. Hopefully you remember anything to the 0 power is simply 1. No variables at all, so our coefficients is just 1. Next, our first row, this is a plus b to the first, which anything to the first power is just itself. So our coefficients become 1 and 1. Next, second, and we did this one quite a bit when we were working in quadratics. This was a squared plus 2ab plus b squared. So our coefficients were 1, 2, and 1. And we can continue to do this, working ourselves down through the systems, and we'll come up with a series of expressions that continue to multiply this binomial of a plus b times the previous set. And when we're complete, we end up with a table that looks like this. Now, the form that is being created on the right-hand side with this list of coefficients is a special tool that's used in mathematics called the Pascal Triangle. And there are many patterns that exist inside of it, but let's take a look at how we can build this on our own without doing this binomial expansion. Here we have an expanded form of Pascal's triangle, taking it out to the 8th row. So if you look, the triangle up through the 5th row is exactly the series of coefficients that we had when we were working previously. Now, how is a single element in the row created? The outer section is always 1. And then to receive any other element in the row, we simply add the two numbers that are above it. So this 2 is the combination of 1 and 1 being added together. This 4 is 1 plus 3. This 15 is 5 plus 10. 56 here is 21 plus 35. So what happens when we expand any binomial is we receive a series of like terms that follow through this pattern. So we can use Pascal's triangle to speed up our work in expanding a binomial. For instance, if I have a plus b to the 8th, what I can do is take this 8th row and it becomes my set of coefficients. So what I would have is 1 plus 8 plus 28 plus 56 plus 70 plus 56 again plus 28 again plus 8 and then plus 1. Now we need to work on our variables. We'll have a in all but the last one, and it does exist in the last one, but it's a little bit harder to see, and I'll explain that here in a minute. And then we have b in all the others. We do not have it in the first one per se, but it is present everywhere else. Now the coefficients, or sorry, the exponents for each term will always add up to whatever row we're on. So we're looking here at row 8, so our exponents always have to add up to 8. Our first one, a, is to the 8th power. And then we count down our exponents. So a to the 7th, a to the 6th, 5th, 4th, 3rd, 2nd, 1st, and then technically it would be a to the 0, but anything to the 0 power is simply 1. Now the b's compensate for what's left. So in our first one, we have a to the 8th. We don't need anything else. Next one, we have a to the 7th, so that gives us a b to the 1st. That way they add up to 8. And we'll continue b squared, cubed, 4th, 5th, 6th, 7th, and 8th powers until we have the full expression. So we can build a binomial expansion using Pascal's triangle. The thing is, we could actually take this and work with these patterns in a real set of binomials. We haven't been working with x plus y to certain powers, but we've been working with like x plus 4 raised to a different power. So let's take a look at how that would appear, how we can work with that with the shortcuts of the binomial theorem and Pascal's triangle. Let's expand the binomial 2x minus 3 to the 4th. Well, let's start by assigning some values. In this a is 2x, and b is negative 3. Now our fourth row of Pascal's triangle went in the form of 1, 4, 6, 4, and 1. Notice the fourth row has 5 terms. So what we're going to have is 1 a to the 4th plus 4 a to the 3rd b to the 1st plus 6 a squared b squared plus 4 a to the 1st b cubed plus 1 b to the 4th. Now what we need to do is substitute in our a and b values. So what we'll have here is 2x to the 4th plus 4 times 2x cubed negative 3 to the 1st plus 6 times 2x squared negative 3 squared plus 4 times 2x to the 1st negative 3 cubed plus negative 3 to the 4th. Then we start simplifying this. And remember, when we have the quantity 2x to the 4th, that means everything there is being multiplied 4 times. So it's like saying 2 to the 4th x to the 4th. 2 to the 4th is 16. So we come out with 16x to the 4th. Next, if we have 2x cubed, 2 cubed is 8. And then we have 4 times 3 is 12. 8 times 12 is 96, and it's negative. So we have a negative 96x cubed. Next, we will have 4. Negative 3 squared is 9. 4 times 9 is 36. 36 times 6 is 216. So we come out with 216x squared. Plus, this comes out to be just 2. And then negative 3 cubed is a negative 27. 27 times 4 is 108. If we double that, we get 216. So we have a negative 216x. Then negative 3 to the 4th power is 81. So we have plus 81. Now rewriting so that our signs are all correct, we have 16x to the 4th minus 96x cubed plus 216x squared minus 216x plus 81. So using the simple patterns found in Pascal's triangle, we can expand a binomial by simply using substitution and following the patterns that exist in the system. So a little bit different way of doing math, but this can greatly speed up how you're able to work with these numbers.